Eu não sei se vocês conhecem, mas é o cara.
All right, thank you. My title is Making Sure Software Stays Insecure. I'd like to start with some news stories as motivation. First, I have a picture of the Umbrella Revolution. These are terrorists in Hong Kong who are attacking the Chinese government. There's a picture here of one of these terrorists. I don't know if you can see it from the back, but he's holding a weapon which he's about to throw at a police officer. I have another picture here of another news story. This picture almost speaks for itself. These are drug dealers. Coffee, for those of you who don't know about it, coffee is a dangerous drug. It is a mind-altering drug. It is something that is addictive. It leads you into more dangerous drugs. It turns you into an axe murderer. It is not a good thing for our society. And these people, Starbucks, they are drug dealers. They sell coffee. This picture has somebody in black and white. Apparently he just escaped from prison. He is a pedophile. He is abusing an innocent young girl named Miley Cyrus, who's only 21 years old. This picture is child pornography, and this is being distributed on the internet. My last example of a news story, The Guardian, in Arabic, Al Guardian. This is an Islamic sympathizing organization which is taking classified government secrets and selling those secrets. They make money by selling secrets to Russia, to China. It's terrifying what these people are doing. So I'm sure you'll agree that we have to stop these people. We have to stop the terrorists, we have to stop the organized criminals, the disorganized criminals, the drug dealers, the murderers, pedophiles. And the way that we can do this is by watching everything and listening to everything. So how do we do this? Well, one way to do this is to watch the entire internet. We collect all of the internet traffic, record all of the internet traffic, maybe not everything, but as much as we can. And then there's a problem. Sometimes this traffic is encrypted. So, how do we make sure this is not a problem? Well, what I'm going to do in this talk is select examples, just a few examples. I was told that I have to stop talking after 3 hours. But a few examples of how we can make sure that encryption is not a problem. How we can make sure that we understand the plain text, the unencrypted data, even if somebody tries to encrypt it. Okay. This is some more stories from another terrorist organization, Al Intercept. Al Intercept has some quotes which I guess are not readable. I'll read a few of these. NSA has these documents. NSA says they want to insert vulnerabilities into commercial encryption systems, IT systems, networks, etc. NSA influences policies, standards, and specifications for commercial public key technologies. I wish I had some heroic music at this point. NSA, watching everything, yay! NSA works with specific named US commercial entities. NSA works with foreign partners, etc. Now, I should say that breaking crypto is not the only thing that you can do. For example, you can break into software. This is maybe even more productive than breaking the crypto. If you can manipulate the software ecosystem, change the software that people are using so that it's insecure, then you can break into cameras, microphones. There must be 1,000 microphones in this room, and then you can listen to everything. You don't need to break the crypto. Something else you can do is put backdoors into hardware. For example, the Chinese government successfully did this according to the US government. The US government says that Chinese routers allow backdoor access for the Chinese military, Chinese intelligence. And you could imagine other people also putting backdoors into hardware. I have one slide of a little bit of clarification. I don't actually believe that we should be backdooring crypto. In fact, I believe exactly the opposite. We should not be creating insecure crypto. We should be creating secure crypto. And some people say that this is a difficult decision. There should be a balance between security and privacy, and so balancing means eliminating crypto. The FBI director would like to get rid of crypto. But I don't believe that this balancing is a reasonable question, because there are human rights recognized in most countries, and these human rights include a right to privacy. And that right to privacy is enforced by crypto. I should also clarify that the examples I'm giving, these are not examples where I know that the government was involved. There's an old saying, I think from Napoleon, which says, never blame the NSA for something that can be adequately explained by stupidity. There's so much bad crypto from stupidity that, well, if you're a government trying to make crypto insecure, you have great cover. There's lots and lots of stupidity, and then if you push things in a bad direction, then, well, it looks just like all the other stupidity. There are a few examples where we know that the crypto systems were manipulated. We know that there was successful manipulation for insecurity. But the examples that I've chosen for this talk are just a thought experiment. What would I do if I wanted to manipulate the ecosystem for insecurity? All right. First example, very productive way to break crypto is timing attacks. For example, there was a paper by Osvik and Shamir and Tromer in 2005 which broke the Linux disk encryption device, dmcrypt. They extracted the dmcrypt key in 65 milliseconds. They had to run a program on the same computer, but, well, the browser could run this. Lots of different programs run on your computer. And without any privileges, they extracted the dmcrypt key. And at that point, they could decrypt the hard drive. Why did this work? Well, if you look at how AES software works, AES software uses tables. It takes a secret byte of plain text and exclusivores that with a secret byte of key, and then looks up that position in a table. Now, the time that it takes to look up data in a table, that depends on the position, the index. If you say x bracket I, the time for that depends on I. Because if you have a cache and the cache only has some data and not other data, then if you look up data from the cache, it's faster. And if you look up data from other positions, it's slower. Actually, there's even more effects. Even for data in cache, there are timing variations. So when AES software is running, it looks up different positions in the cache. It actually affects what the cache state is, and that affects timings of the AES software and timings of attack software. The attacker can figure out all of these effects. I won't go through the details, but the attacker can work backwards from the timings of attack software to figure out the AES key. And that's what this paper did. Another example, 2011 paper from Brumley and Tuveri. This one extracted ECDSA keys from OpenSSL. The idea here was not x bracket I leaking information about I. The idea here was if I. That leaks information about I. And the timing of an if depends on the branch condition, depends on the I. There are many, many, many examples of this. If you write code naturally, then you end up with many secrets which are used for branches, many secrets which are used for array locations, load addresses, store addresses. And then these secrets influence timings. And then the attacker can see timings The attacker can figure out the secrets. Recent example, a 2014 paper, is extracting your Bitcoin secret key from 25 signatures. So if someone's running a program on your computer while, for example, in the browser, while you're doing Bitcoin computations, then they know your Bitcoin secret key. If you do only 10 signatures, then it's okay. Okay, so how can we manipulate this crypto to make sure that there are timing attacks that we can exploit? Well, one good thing to do is deny that the attacks work. And if the terrorists, in crypto, there's names for the terrorists. The terrorists are called Alice and Bob, or Muhammad and Muhammad, but I'll use Alice and Bob. So Alice and Bob, if they believe that they're secure, and they're not secure, then we can break into their communications. For example, here's an example of a denial. NIST, the US National Institute of Standards and Technology, they have a report on the development of AES. And in that report, they mention timing attacks. And they say to stop timing attacks, make sure that every operation takes the same amount of time. And then, of course, if the attacker sees the time, the attacker doesn't learn your secrets. And they say, the red at the bottom there is saying, table lookup is not vulnerable to timing attacks. They claim that table lookups take constant time, which is wrong. And that's exploited in some of these attacks. Here's a different example of denial, the TLS 1.2 specification. This says there's a small timing channel which is not believed to be large enough to be exploitable. This is like that moment in a movie where you see that there's the well-protected barrel full of gasoline and the terrorist is walking next to the gasoline, and you just know that there's going to be gunfire and the gasoline's going to blow up and the terrorist's going to die. Yay! So it's not believed to be exploitable. Yeah, we know there's a problem, but we don't think that the problem is exploitable. So, of course, it blows up, it gets exploited. This is the Lucky 13 attack, which breaks TLS, finds your TLS plaintext. Now, the terrorists, Alice and Bob, could maybe protect themselves, because you can write software which, for example, uses XOR, AND, OR, shifts. Very simple instructions that have no impact on timings. You have to be a little bit careful. Some CPUs, if you multiply, it takes different time. Actually, some CPUs, even if you add, it takes different time, depending on the inputs. But if you're careful, if the terrorist crypto developers are careful, they can write software which takes constant time, has no impact on timings. And then we're in trouble. Then we don't see the secret key from the timings. So how do we react to this? Well, we tell people that it's too complicated and too slow to write software which takes constant time. It's important to use if. It's important to use X bracket I. Now, maybe people don't believe that, so then start throwing money at it. Start putting more money into variable time software. OpenSSL. Most OpenSSL code takes variable time. They're trying to put in some constant time software, but it's a very slow process and it doesn't work very well. So put money into libraries that don't actually stop attacks. And then maybe tell people, oh yes, we're trying to stop the attacks, really. Here's some countermeasure. OpenSSL has some code which says it's stopping timing attacks. Really, it's making the code more complicated, so the timing attacks are not so obvious. If it's complicated, it must be secure. It's not actually stopping the problem. And if you're really careful, you can make a timing variability, which is very hard for researchers to break, but very easy for Bluffdale, big NSA supercomputer, to break. And then you keep denying that anything better is needed. For example, there's a 2012 paper by Maury and Kilvedi and Shaham, which says are AES x86 cache timing attacks still feasible? And the basic answer in the paper is no. It's really hard to do AES timing attacks now because there's multiple cores and there's prefetching and there's virtual machines. And well, then there's a 2014 paper which says that you can still break AES with timing attacks. Here's the really scary possibility. Maybe the terrorists don't use AES. AES, there's a trade-off. If you do a simple AES implementation, if you do a fast AES implementation, it will take variable time. If you do a constant time AES implementation, it's complicated, it's slow. But there are other ciphers where if you change from AES to, for example, Serpent. Serpent is a very respected cipher, which is very easy to implement in constant time, and it's reasonably fast. In fact, on current processors, I think it's even faster than AES. Unless you build AES hardware, Intel has Core i5, Core i7 CPUs with AES hardware. In those CPUs, AES is faster than Serpent software, but imagine if Serpent had been chosen as AES, then today we would have Serpent hardware on those chips. And in software, Serpent would be more secure. Okay, so this would be a real problem for us trying to break into the crypto. So what do? Make the wrong choices for standardization. When you standardize something, say, AES, we're going to choose Rheindal. We're not going to choose Serpent. Even though Serpent looks more secure, here's some processor where it's slower. So we'll choose Rheindal because it's faster. And so they chose Rheindal. And then once Rheindal is the AES standard, then you tell everybody, oh yes, the standard was chosen for security. Even though the documents clearly say that the AES standard was not chosen with security as the top priority. The AES standard was chosen as a balance between speed on some platforms, speed on other platforms, flexibility, security, and it was not prioritizing security. But once you have the bad standard, then you tell people, this standard is the only secure cipher. And so you must use AES. You must not use Serpent. Here's another fun example, padding oracles. How many people here run HTTPS servers, TLS servers? I see many hands. Have you upgraded to turn off SSL v3? I see some people saying yes. Okay, good. Yeah, so this all started with Leichenbacher in 1998. He was doing what are called chosen ciphertext attacks. So he took an RSA implementation, standard SSL RSA implementation, and he gave it many copies, 1 million copies of the same ciphertext with little changes. And then he watched the responses from the server. Some of those would give an error message, some ciphertexts would give a different error message, and there was some pattern from this. What happens inside SSL, when you do RSA decryption, you do, well, there's some power modulo n, which is p times q, there's some mathematical thing, and then you check some padding. And if the padding is wrong, you give one error message. And if the padding is correct, then you check some more complicated type of integrity. And then you give a different error message if it's a forgery. So he sent 1 million messages. Some of them would give error message 1. Some of them would give error message 2. And from the pattern of error messages 1 and 2, he would figure out the original plain text. This is the same kind of thing that's exploited inside SSL today. The general idea to make these things exploitable is you want to have forgeries processed with as many secrets as possible for as long as possible. What's bad is if the terrorists, bad for us, is if the terrorists throw away forgeries immediately. What we want is for them to let the forgeries sit around and have them interact with secret data and then send us error messages, and then we can see what happened. What was the original plain text? Maybe we can figure this out. And so this is what's happened with Beast and Poodle and other padding oracle attacks. It's also used, for example, to break IPsec. If IPsec is configured without authentication, it's breakable. Here's another example. The original Netscape SSL had only 47 bits of randomness in their secret keys. So you could just try 2 to the 47 keys, not very many, and then you would figure out, aha, this is the key that was encrypting the secure transaction. Another example of a randomness failure, Luciano Bello, or Besho, I guess, was finding that in Debian and Ubuntu, there was a mistake in the randomness generation code. Someone had removed a critical, subtle line of randomness generation code because I think Valgrind complained about it. As a result of that, the randomness was only 20 bits, or 18 bits, or 17 bits. Very little randomness in the Debian and Ubuntu secret keys for SSL and I think also SSH. Another example from 2012. Various teams found 0.5% of all secret RSA SSL keys on the internet. Tens of thousands, something like 20,000 SSL keys. They factored 1024-bit RSA. And the reason was that those prime, the P and Q inside those RSA keys, were not generated very randomly. In fact, they were so non-random that the P's would sometimes be exactly the same between two different keys. Okay, so this looks like things going wrong, and that means for us as the attackers, we want this kind of thing to go wrong. So how do we promote randomness failures? Make sure there's lots and lots of randomness code. Make it complicated, make it hard to audit, hard to verify. You want to have every application having its own randomness generation. Netscape, okay, it's not used now, but now Firefox should have its own randomness generation. Chrome should have its own randomness generation. Internet Explorer, separate randomness in every program. OpenSSL has its own randomness generation. The operating system kernel. Everybody has separate randomness generation. You say, first of all, this is important for speed. You can make any stupid crypto decision if it's fast. It's clearly fast to have randomness inside the program. Don't talk to some other program. Don't have a single centralized randomness generator. Have every program doing its own randomness, and have every program doing it differently. If you're writing a secure telephone program, you're listening to the microphone, and that's random. So use the microphone for randomness input. If you're writing a network, secure network program, maybe the timing of network packets, that's random, right? And the attacker will never figure out the timing of network packets. So use that for randomness. Every program should have its own separate randomness generation. And then many of these programs will make mistakes. Many of these programs will have bad randomness, and nobody will find all of these problems because there's so much code to review. At the bottom of the slide, I have dual EC. Now, this is one example where we know that it was an NSA backdoor. NSA paid the RSA company $10 million to implement dual EC by default. Dual EC is a backdoored, NSA backdoored random number generator. But, well, this is unusual. Most of my examples, we don't know if they are malice or just stupidity. Yes, I also have at the bottom of that slide, provable security. This is another good thing to make people make stupid decisions. Speed, complexity, provable security. You can argue for these things very easily. All right, what if Alice and Bob realize that there's a problem? What if Alice and Bob, the terrorists, take all of the inputs that they have? They take saved state from flashing the device, they take input from the network, input from the microphone, input from the camera, the access point, power level for the wireless. They take everything they can think of, and they put it into one central randomness pool. Well, then we're in trouble, because we need all of those randomness sources to be predictable. We need everything to go wrong. If they hash lots and lots of inputs together, then we need to predict all of those inputs to predict the randomness. Also, if they design a sensible, centralized system, then they can verify that small piece of code. And then we'll really have trouble figuring out the random numbers. So what do? Well, speed is again a good answer. We tell people it's too slow to use dev random. It's too slow to use dev urandom. It's too complicated to use dev random, dev urandom. And putting inputs into these things, oh, that's too complicated. It's only a few lines of code, but it can go wrong. It's much safer to put randomness into your application. Do your own code for randomness, because you'll do it better. Ha, ha, ha. You can also take the centralized systems like random and urandom and put in little mistakes into the design that make them hard to use or scary from a security perspective. Dev random does not work. It is too slow. Dev urandom works, but if you never put any inputs in, it gives you non-random data under Linux. BSD gets this all right, but okay, tell the terrorists to use Linux because everybody else uses Linux. Okay, these speed arguments are obviously kind of stupid. I mean, randomness generation, you generate occasionally a random number. So why should anybody care about the speed of randomness? Slow randomness is fine. Slow centralized randomness is fine. Okay, so how we tell the terrorists that randomness has to be fast is we use as much randomness as possible. Every opportunity we have to use randomness, we use randomness. And then it's important for randomness to be fast. For example, the DSA and ECDSA signature systems. Every signature, you have to generate a random number. Now, this doesn't need a central random number generator. It doesn't need a decentralized random number generator. You could just hash your secret and the message that you're signing, and that gives you something that looks random. So you don't need randomness at all. You can simulate randomness with a hash function. But DSA and ECDSA say, use a random number generator, an approved, federal government approved random number generator. There's a nice quote from Rivest in 1992. He said that this randomness gives the poor user enough rope to hang himself. People have occasionally complained about these badly designed standards, but the standards are still there, and, well, you know about the PlayStation 3 break from Fail Overflow, which found the PlayStation 3 signing key exactly because of this misdesign of DSA and ECDSA. Sony, in the PlayStation 3, repeated the random numbers, and then game over. Another type of way to break crypto is the traditional kind of break-in crypto that you see in papers. When academics talk about attacking crypto, they usually talk about how fast is an attack that computes collisions in a hash function, or computes pre-images, or computes factors, or some mathematical computation. And sometimes that computation is doable. For example, MD5 in 2004 had collisions discovered. 2008, a team created a rogue certificate authority, their own certificate authority for TLS, using MD5 collisions. In 2012, Another attack against MD5 was carried out by Flame, successfully breaking into some terrorist computers. The terrorists in this case, that's Iran. And Iran says they're building nuclear reactors for peaceful purposes, but we know they're terrorists. And Flame broke into those computers. Yay, Flame. Now, in 1996, cryptanalysts said MD5 is scary. MD5 is bad. You should not use MD5. That was in 1996. But still, 16 years later, we were able to break into computers using MD5 attacks. So how do you keep a broken crypto standard around? Well, you standardize it. You say it's very fast. You say it's compatible. It's what everybody else is using. It's interoperable. You need to use MD5. Today, in SSL, you need to use MD5. Here's another example, DNSSEC. I looked at the IP address for dnssecdeployment.org. And this is signed with DNSSEC, with a 1024-bit RSA key. If somebody factors the 1024-bit RSA key, then it's game over. And they can then fake the IP address. Well, okay, it's not clear how that's related to breaking the whole system, but let's just look at what DNSSEC does. DNSSEC still uses RSA 1024. Actually, this 1024-bit key is signed by a 2048-bit key, which is signed by a 1024-bit key, which is signed by a 2048-bit key, which is signed by a root 1024-bit key, which is signed by a root 2048-bit key. Very strange. Already 10 years ago, cryptanalysts said 1024-bit RSA is breakable. Shamir, the S in RSA, said 1 year, $10 million, he can break any 1024-bit RSA key. So you should stop using RSA 1024. Should not have been using it even 10 years ago. But DNSSEC says speed. Again, speed. Great excuse for bad crypto. Here's a quote from the DNSSEC documents. There's a trade-off between the risk of key compromise and performance. Really, not that many people use DNSSEC. Who would bother breaking DNSSEC anyway? So, how do you make sure that the terrorists are making this kind of decision, that they're using MD5, RSA 1024, other breakable cryptographic standards? Well, you can tell them there was this paper from 20 years ago that said that RSA 2048 was very slow. Yeah, there's these elliptic curves, but those sound really complicated, and we're not going to benchmark those. And yeah, some people say elliptic curves are fast. No, they're wrong. For example, here's an EU project called Preserve. This is a project that's received millions of euros from the European Commission. And they say that they're protecting vehicle-to-vehicle and vehicle-to-infrastructure communication. So your car on the highway, you step on the brakes, and then the car sends out a message to all the cars around saying, I've stepped on the brakes. And maybe those cars can warn you and say, you better step on the brakes. What is the Preserve project spending millions of euros doing? Well, the answer is at the bottom. They're building a cryptographic coprocessor. And what is this coprocessor doing? It's verifying signed messages. Why do they need a coprocessor? Why do they need millions of euros to develop this? Because they say a Pentium D processor is too slow for 1,000 signature verifications per second. So they need to build special hardware to process 1,000 signatures per second. Now, I find these numbers very strange because, for example, let me just focus on some number in the middle here. If you want to do verification using the curve 25519 elliptic curve, signature verification. You can do that 1,600 times, 1,600 times per second on a Cortex-A8 processor. Now, the Cortex-A8, is this a fancy, expensive graphics card? No, this is an ARM processor. It's an old ARM processor. This is an iPad 1 CPU, or a Samsung Galaxy S. That used a 1 gigahertz Cortex-A8. Today, you can buy this processor for $5 from Allwinner, Chinese company. Or you can buy it for $12 from TI, with backdoors built in. So this $5 processor can do more than 1,000 signature verifications per second using state-of-the-art ECC. But here's millions of euros being diverted into a stupid hardware project to do something which this $5 processor can do. What happens if Alice and Bob realize that they don't need insecure crypto? If they realize that secure crypto is fast enough, then we're in trouble. Then we can't break RSA 1024 if nobody's using it. So how do we discourage these terrorists from using the fast crypto? Well, we say, oh, ECC, elliptic curves, nobody's looked at elliptic curves. Are those really the standard? DNSSEC, everybody uses RSA. So RSA is the only secure thing to do. Yeah, maybe some people want to put elliptic curves into these standards, but really, you should only trust RSA. Maybe the terrorists say they really, really want the good crypto, the secure, fast, state-of-the-art crypto. Okay. We have to standardize it. We have to allow it. We have to give them the good crypto and 99 other options, which are all bad. TLS has many, many options for your crypto, and most of them are bad. Most of them are breakable. Some of them are slow. The user is not going to configure SSL correctly. The sysadmin who's trying to set up SSL has so many options, most of them are bad, it's going to be a mess, and we can break it. Often people will say that having many options is good. This is a great strategy for us. Many options is cryptographic agility. If you don't like RSA 512, you can switch to RSA 768. That's cryptographic agility. I prefer to call this cryptographic fragility. The cryptography is fragile. It's breakable. It's going to go wrong. And that's what we want. If you have agility, then you can say that it's not so bad to use RSA 512. It's not so bad to use MD5 because we can change to something else because we have agility. So the users keep using bad things. One more example and then I'll finish. Pre-computed signatures. So this cryptographic fragility, trying to make cryptography fail, have many bad options, many complicated options. That's a very useful technique. You can build this into higher levels of the cryptographic system. I've only been talking about, well, lower levels of crypto, but you have to integrate crypto into applications. And let's look at a way to make that fail. When you want to have secure communication between Alice and Bob, when the terrorists want to have secure communication, well, you don't have to give it to them. What you can tell them is, let's focus on one problem at a time. Let's first have authenticity, integrity for your messages. That's the most important thing, is being sure that you're talking to Bob. And then we'll put in crypto for encryption later. So there's the easy problem of signatures and the hard problem of encryption. And why is encryption the hard problem? Well, here's an example. In the IETF TLS working group, there are discussions of encrypting SNI. When you connect to an HTTPS server, the name of the specific website that you're connecting to is sent unencrypted. That's SNI. Now, in the TLS working group, there are proposals to encrypt the name of the website that you're connecting to. So if there's a site with thousands of domains on it, the attacker doesn't see which name you're connecting to. Are you connecting to diabetes.webmd.com or firstaid.webmd.com? You could encrypt SNI, but the TLS working group says there's no reason it's not useful to encrypt SNI because the attacker can see the domain name by watching DNS. Now, in the DNS working group, there are proposals to encrypt DNS. And they say it's not useful to encrypt DNS because the attacker can see the name in SNI. So making information private is hard. If you just want to sign something, then having one signature and one non-signature is usually okay. If you want confidentiality, having encrypted and unencrypted is a disaster. So argue that having signatures first is the easy thing, and then pre-compute the signatures. This is a speed argument. Again, use speed to make bad crypto. Use speed to tell people that they cannot sign data online. They must sign data offline and then save the signatures in a database because then it's faster to look up the signatures from the database. Make sure that the protocol is consistent with pre-computing signatures. And then that causes all sorts of problems in the protocol. For example, what happens if you have dynamic data? DNS data is often generated dynamically. Web pages are generated dynamically. If you pre-compute signatures on data, then that data is hard to generate dynamically. The protocol makes it hard to use dynamic data. Suppose that somebody asks for a page that doesn't exist, or asks for DNS data that doesn't exist. You don't have a signature on it. So what do? This makes the protocol complicated, makes it hard to deploy. What if somebody wants to protect themselves against data being rewound, data going back to old data? Can the attacker change data to old data? Or can Alice and Bob be sure that they're seeing fresh data? Well, if you have pre-computed signatures, it's very difficult to make sure that those are fresh. And these problems make the protocol more and more complicated and more difficult to deploy. And then, while you're still working on signatures, obviously the hard problem of encryption, you shouldn't try to encrypt anything. And so today, most web pages are not signed, not encrypted. Most DNS data is not signed, not encrypted. All right, last slide. Just a few more things that I decided I would not have time to talk about. You can make sure that your crypto funding and the people who work on crypto make sure that that's not actually useful crypto, or maybe slightly useful, but not actually getting in the way. Remember, the objective here is to stop pedophiles and stop drug dealers. And if there's going to be money spent on crypto, it's okay if the crypto lets us catch everybody. If the crypto lets us watch everybody, listen to everybody. So, okay, spend lots and lots of money on crypto that doesn't solve the problem. For example, it's really nice to have people setting up crypto where they're encrypting data to Google, and then Google sees the plain text. That means that everybody who has enough money, everybody who has enough political power sees the plain text. That's the kind of crypto that we want, to make sure that people can't actually communicate privately. It's nice to set up systems which are protecting against passive attackers, but are easy to break for active attackers. If you have, for example, TCP crypt, and then you run TCP dump passively, then TCP crypt is encrypting lots of data. But if you're an active attacker, if you forge packets, then TCP crypt provides no security at all. This is good kind of crypto. We want crypto that's easy to break by just doing some easy active attack. And finally, make sure that your success measures allow you to not have the internet encrypted. Make sure that people say, yes, we have crypto, we have interoperable clients and servers, they're talking to each other, it's deployed on hundreds of machines. Yes, we have working crypto. The rest of the internet is unencrypted, but you tell people that they've succeeded at doing crypto, even though the entire internet, almost the entire internet, is unencrypted. That's it. Thank you for your attention.